Welcome to Faith and Science. I'm Dr. John Ashton. I think when someone gives us a lovely smile, it can be so encouraging and uplifting. And of course, when they do that, they're showing us their teeth usually. And the teeth in the mouth, actually, we take them for granted a lot of the time. But there's still a lot of research being done with regards to teeth and people understanding the dental processes and so forth. And one of the reasons, of course, they're working on this is in efforts to combat tooth decay at the present time. But the teeth themselves are really powerful evidence, in my view, for creation. And, of course, tooth decay, really, in my view, is a disease of civilization. I remember reading studies where young people, children that grow up just eating unprocessed foods and even chewing on things like sugarcane, had perfect orthodontal development and did not tend to develop dental caries, the same like we do in the Western cultures where we tend to have a lot more refined food, even though we have things like, toothbrushes and things like this. So it's quite fascinating, our teeth and how they're structured. Of course, we start off our teeth develop as children. We have what are called our baby teeth, where we get we have 10 of those, 10 in the upper jaw and 10 in the lower jaw, and then these, of course, fall out in due time and they're replaced. And in adults, we hopefully end up with 16 teeth up in the upper jaw and 16 in the lower jaw. Of course, not everyone. The last teeth, my understanding is these third mandibles, they develop, they're, I think, called our wisdom teeth. And, of course, not everyone develops those. And, of course, some people develop actually extra, the fourth and fifth molars. They're fairly rare, but they're referred to as, hyperdontia, the fourth and fifth molars. So it's interesting, of course. Males generally have a larger jaw and females a smaller jaw. And, of course, but it's amazing how the teeth all fit and they can look so nice. And, of course, it's hard to imagine how such a structure could arise by random blind mutations. And, of course, we're just looking at human teeth today, and, of course, so many different, all the, the mammals and so forth have different teeth, and fish and so forth, and all have different properties. But just looking at human teeth today in my talk, and it's something that I've found actually quite fascinating. Of course, we've got, of course, the enamel on the outside of the upper part of the tooth, and in under that is the dentin, and that's the substance between the enamel and either the cementum, which is a part on the side of the tooth, and the pulp chamber. And actually, the dentin is secreted from the dental pulp. And that's often where we get the decay. Of course, the enamel is the hardest structure. Tooth enamel is actually the hardest material in the body, and I'll talk about that in a little bit more, of course. And the cementum is a type of specialised bone substance covering the root of the tooth. And it's about 45% inorganic material and about a third organic material, and then, of course, and about 20% water. And then, of course, we've got the tooth of the teeth. And the dental pulp, which is in the centre of the tooth, is just soft connective tissue and has blood vessels and, of course, nerves. And that's why we need anaesthetic if the dentist needs to drill into that material when he's doing a filling. So the teeth are made up of these interesting parts. There's quite a lot of structures, as I said, with the blood vessels and everything in the structure of the teeth. But one of the things, of course, that I find most fascinating is tooth enamel. Now, tooth enamel, and one of the reasons I find most fascinating, on the Mohs scale of hardness, the tooth enamel has a hardness of 5. And it's interesting that untempered, so non-hardened, iron and steel only has a hardness of 4 to 4.5. So the higher the number, the harder the material. And it's actually just less than glass, which has a hardness of about 5.5 to 6. So it's quite amazing material. Really quite an amazing material. And it's interesting that our teeth really are surprisingly tough, and they usually remain uncracked through decades of biting and chewing. Yet the surface coating, which is called enamel, and as I've just said, it's the hardest substance in the human body, but yet it's also brittle. But yet it has a special structure that minimises cracking. And, of course, this structure, this enamel, coats the main tooth material, which is the dentine. It's sort of the equivalent to, ivory, I suppose, where ivory is simply solid, more solid dentine. It's involved actually in protecting the enamel as well from the inside. It's interesting if you think of glass, if you have a windscreen on your car, once a tiny crack starts, it doesn't take long to propagate through the material. But it was interesting, a study that was done applying quite a large loads to different types of teeth, like human teeth, has shown how the enamel has a number of features that prevent cracks spreading. And so scientists have been looking at the structure of teeth quite recently, actually, to try and understand better how they can improve repairs to our teeth. I can remember when I was a boy, I think it was first year high school, I won a prize. I won a dental competition. And that prize I was taken down, and there was a winner from every school, and I was the winner from my high school, and we went through the Colgate factory. But it was interesting. I hadn't had to go to the dentist. I didn't have any cavities, but when my dad died a couple of years later, we moved into a town where there was a lead smelter. The largest lead smelter in the southern hemisphere was nearby, and it turned out, we didn't know at the time, but there was massive levels of lead in the atmosphere that we were breathing in. And it was interesting, within a few years, I developed a number of cavities in my teeth, even though I was cleaning my teeth. And I subsequently had to have mercury fillings. And it was interesting, a few years later when I was studying, when I was at the University of Tasmania doing postgrad studies down there as a research fellow, one of the other guys there is working on his PhD on graphite furnace atomic absorption, and he was developing back then some of the first methods for analysing lead levels in blood. And I can remember that he, for a control sample, he thought he'd take some blood for some children in a small country town. But when he analysed their blood, he found that the lead levels were nearly as high as children living next to freeways in Los Angeles. And, of course, this was back in the early 70s. Of course, that was back when we had leaded fuel. And he was amazed what had happened. But, of course, it was an apple growing area and they were using lead arsenate sprays. And then, of course, it was some years later, not until I think around the 1990s, that I think it was research out of the University of Madrid showed that lead softened teeth. And so this was, again, as I realised then, that's why my teeth went to pieces. And, of course, lead, as valency 2, can replace calcium, which is one of the components of our teeth, because essentially the enamel is a type of calcium phosphate, crystalline calcium phosphate that is extremely hard. And so it's interesting that what happens is with our teeth, it would seem, and this is still being studied at the present time. How our teeth form and grow is still not fully and completely understood. But it seems that as the teeth develop, there are a number of small flaws develop, or little cracks, and these cracks are then filled. They form little sort of defects where the enamel joins the dentine, and thus these little cracks, as they're forming, could form the basis of larger cracks but they're deep within the tooth, so they're protected from decay. But the crack actually stabilises because of stress shielding from actually other cracks. So it's interesting that these small flaws actually work like a forest and suppress the cracks from developing further. It's an amazing system. So there's quite a bit involved. So, and I'll talk a little bit more about these cracks in a little bit. But the other factor that we need to understand there is that there's an arrangement of crystalline rods, which are the basic units of the enamel, and bundles of these rods crisscross each other on the length of the enamel dentine junction to the enamel's outside surface. So, it's a special pattern that forms that also hinders the crack propagation. Now, so this crack growth is hampered by this basket weave type microstructure of the enamel. And it's interesting, there's also a self-healing process where organic material, protein materials that acts like a glue, actually fill the cracks that have extended from these little tufts, these little starting point cracks at the junction of the dentine and the enamel. And these little tufts, these little cracks also become closed by these particular proteins that actually glue that together. So it's amazing. So you'd think, oh, well, the cracks would be a fault in design. But no, by having those cracks, which are then subsequently filled with this glue, this protein glue, it actually makes it an even stronger structure, stronger crystalline structure. And secondly, another point that was found out was with this research, and this was research, this particular report and this was research that was published in literature back in 2009. For example, in the Proceedings of the National Academy of Sciences on the 13th of April 2009, there was a paper titled Remarkable Resilience of Teeth. And there are a number of reports about this research. Another one appeared in Science Daily on the 20th of April 2009 called Cracking the Root of Tooth Strength. It's amazing. So you'd think, oh, okay, these little cracks there, there's a design fault. But no, because they become filled with this glue and resin, they make them actually stronger, or this organic material which acts as a glue, this organic protein material. And it's interesting, the report summarises, and I'll read it to you, and this is from the report. This is the first time that enigmatic developmental features such as enamel tufts have been shown to have any significance in tooth function. And that was from the lead researcher, Paul Constantino. Crack growth is also hampered by the basket weave microstructure of enamel and by a self-healing process whereby organic material fills the cracks extended from the tufts, which themselves also become closed by the organic matter. This type of infilling bonds the opposing cracked wall, which increases the amount of force required to extend the crack later on. And I think this is one of the fascinating things about how could blind random chances come up with such an incredible design, let alone the functional shape, let alone the uniformity. And as it was just pointed out to me prior to giving the talk, it's fascinating. Our teeth all grow to exactly the same height. They all grow in just the right place. They, of course, unless we have some sort of genetic defect. But this is, powerful evidence, again, for coordinated design, not random chance mutations. Another aspect, too, is that the tooth enamel itself is really hard to replace. And, of course, I found this out when, again, I was subject to this tooth decay after being exposed to the lead. And I then had mercury fillings. And, of course, at the time you could have gold fillings as well. But, Dad had died. I was living, I was a student. My mum was on the widow's pension. So, and fortunately, the dentist didn't charge us because Mother was on the pension. He was a very, very kind man. And, of course, gold was often used. And then, of course, later they developed the ceramic type materials as well. But it's interesting, the tooth has to be so hard because that's what we chew things with. And, of course, we want our teeth to last our lifetime. And it's fascinating that the natural biomineralisation processes that produces the tooth enamel is a complicated, of course, and well-aligned apatite structure, which is a calcium phosphate type of calcium phosphate. And as we said, it's very hard in the laboratory to create this amazing structure that is in tooth enamel that I've just explained, this basket weave structure, the little cracks that are filled with the protein that serves as a glue and so forth. Because as this calcium phosphate structure is developing as the tooth grows, there is particular cells called ameloblasts, and they produce these special proteins that harden the famous really tough external coating of our teeth. So when you think about it again, you have to, by random blind mutations, produce a genetic code that is going to produce these proteins through a whole range of chemical reactions that are governed by enzymes and specific chemicals to produce these proteins in just the right place at just the right time so that these teeth can develop. And I think we can see, again, that these sort of effects just and natural changes don't occur as a result of blind random mutations to produce the DNA to produce all the materials, and our DNA encodes for all these different materials that make up just our teeth. And it's interesting that in 2019 was one of the first times that scientists were able to sort of grow an enamel coating onto teeth. So this work was actually published in a paper that was published in Science Advances in 2019 in Volume 5, Issue 8. And it was titled The Repair of Tooth Enamel by a Biomimetic Mineralisation Frontier Ensuring Epiaxial Growth. And it was by C. Shao, S-H-A-O, and 11 others. It was also, you can also read about it it was also published on the 3rd of September 2019, sciencealert.com. And the title of that article was Scientists Have Developed a Genius Method That Actually Regenerates Tooth Enamel. Well, it actually didn't regenerate totally what tooth enamel is like, but they were getting close. And another one was published in theguardian.com, 31st of August 2019, scientists discover a way to grow tooth enamel. And so what actually, and you had all these breakthroughs, and they were by researchers at the Zhejiang University in China. And what they'd done was they, using an ingenious method involving the coating of volunteers' teeth with a gel containing calcium phosphate ion clusters, they managed to generate a thin 2.7 micron layer of enamel over a 48-hour period. But, of course, to match the natural tooth enamel thickness and to tackle cavities, the researchers really have to improve on this by several hundredfold, not in thickness, but in terms of the actual structure. But so there we can see, and often these things are, really written up or publicised by the media as a little bit better than they are, but at least it was a start. But one of the challenges is to grow this material again with the cracks in it, with the glue and with the crisscross structure. So this is, you can see, for something like this to arise by chance, and then we've got the top scientists working to try and work out better ways that we can replace teeth, and yet we still cling in teaching these scientists to the theory of evolution. One of the other things that comes up, of course, is our wisdom teeth, and these are those last set of teeth, or the third molars, as they're called. And they're called, of course, wisdom teeth because generally they erupt in the late teens and early 20s. And, of course, the age of 21 was traditionally the age of wisdom. So as far as I understand, my wisdom teeth hasn't come through, but my wife had to have her wisdom teeth out. And, of course, being a woman, her mouth was a bit smaller, I guess. And but it's interesting that the orthodontist John W. Cuozzo, that's spelled Cuozzo, and he's quite a famous dentist. I think he was involved in working on the team that years ago helped confirm Hitler's remains, I think, from teeth. And he did quite a lot of work on Neanderthals and their teeth. And he reports that they had, of course, much larger jaw bones, and they also had much larger teeth. And also studies that he did looking at skulls and that have been excavated from hundreds of years ago compared to modern day teeth structures. He notes that 300 or 400 years ago, it took a child 13 years to reach the stage that our children reach today in 9 and 10 years, because we have more rapid maturation today. But what he says is that these facial bones, although children are maturing in many other ways, the facial bones are maturing at the same rate, and they need more time. And so this is part of the reason that he feels that people can have a lot of problems with their wisdom teeth. And it's not a never evolutionary thing. It's probably, in times past, in the Neanderthal times, said the jaws were bigger, there was less processed food, they had a different orthodontic development. Of course, there's also the issue that sometimes raised, well, if the patriarchs lived for 900 years, how did their teeth last that long? Well, we don't really know for sure, but obviously they were, still able to eat. But one of the things that we one of the things that is associated with the Neanderthals is that they had pterodont molars or bull-shaped teeth, and they had much larger teeth, and it's believed that these larger teeth were, would enable them to last much longer as well. And it's interesting, Jack Cuozzo states that he actually still sees children with the Neanderthal-type pterodont molars. And he noted also that these children often come from families with a history of longevity. And so, again, also there's, and as I mentioned right at the beginning, there's also evidence of extremely rare instances of people growing a third set of teeth in their adult years. And so we don't know in the past, when people did live a long time, whether genetically they continued to develop teeth. But I think what we can conclude is that our teeth are amazing evidence of design. Just all the blood vessels, all the different components, all the enzymes that are involved. And they could not possibly have arisen by blind, random mutations. They are evidence of a loving Creator God that wanted us to smile and bring the blessings of smiles to those around us. You've been listening to Faith and Science, and if you want to re-listen to these programs, remember, you can Google 3abnaustralia.org.au, click on the radio button and listen there. I'm Dr. John Ashton. Have a great day.
You've been listening to a production of 3ABN Australia Radio.